10.3. Solve quadratic functions by factoring. In this lesson, we'll look at how to solve quadratic equations by factoring, relate a quadratic equation with a quadratic function, and solve radical equations that lead to quadratic equations. A lot of fun stuff here. Let's start by seeing how we could write a quadratic equation from a word problem. Let's say you have two consecutive integers that have a product of 20. What are the integers? Consecutive is a really important word here because it tells us that if one of the numbers is x, the next number will be x plus 1. And we know that when we multiply those together, we're going to get 20. So we can write the following quadratic equation after we distribute the x over here. X squared plus x equals 20. Now, in order to write this in standard form, we need to have it in the form ax squared plus bx plus c equals 0. So we're going to move our 20 over, minus 20 on this side, to put ours into standard form. X squared plus x minus 20 equals 0. So now what I have is a quadratic equation that's written in standard form. Now, in order to talk about how to work with this, we need to talk about the zero product property, which is an easy property that you probably already know, but maybe don't remember by that name. What that tells us is that if you multiply a times b, and that equals 0, then either a equals 0 or b equals 0. Pretty logical, right? So using this zero product property, let's go back to our quadratic equation here. If this equals 0, that means one of the factors of this equation equals 0. So we need to factor it, and we know how to factor trinomials, lucky for us. We know to do a factor sum table, and we know we're finding factors of negative 20 that are going to sum to 1. And hopefully 5 and negative 4 come to mind that sum up to 1. And we'll go ahead and draw out our factors, x plus 5 times x minus 4, but we're still equal to 0 here because we have an equation. So either x plus 5 equals 0 or x minus 4 equals 0. So we're going to solve both of these for x. Here, x would equal negative 5. Here, x would equal 4. Then we're going to go back to our initial equation, which was x times x plus 1 equals 20. Now we're going to try out our solution. So I had a solution of negative 5. I had a possible solution of 4. And let's see which of these works. So I've got 4 times 4 plus 1. Does that equal 20? 4 times 5. Yes. So that works. How about the other one? Negative 5 times negative 5 plus 1 equals 20. Negative 5 times negative 4, yes, that works. So both of these are solutions to the equation. So we write the solution set then as a set, so we need the braces, and we always go lowest to highest in our set, and we end with braces. So this is my solution set to the quadratic equation. Now what's neat about these two solutions is that if you were to take this quadratic equation and write it as a quadratic function, which would mean we would take the same numbers, but we now equate it to y, and we would graph that parabola, the x-intercepts of that parabola would be those solutions that we found, right? So this would be a positive 4, and this would be a negative 5. Obviously, my graph here, is not correct. I'm just showing you as an example. So these solutions then are called roots of the equation, if you're referring to the equation, or zeros of the function, because those are the spots where the y value equals 0, right, at both of those values. So to recap then, the solutions of a quadratic equation are the x-intercepts of the quadratic function. So think about when we were talking about x-intercepts in the last lesson, you can have 2, you can have 1, or you can have none. And you'll find the same thing is true for the solutions of the quadratic equation. You can have 2, you could have 1, you could have none. So let's look at an example of where we might come up with none. If we take this quadratic equation, minus 5, and we go ahead and try to factor it, use our zero property, and identify some solutions here. We make our factor sum table. We need factors of negative 5 that are going to sum to negative 2. So we think, let's see, 1, negative 5, no, negative 5, 1, no. Oh, that was the same thing over again. I could have done negative 1, 5 to do something different. So that guy's negative 4, that one's positive 4. I can't do it, right? So this is what we would call prime for our, trinomial if we were doing it. What that means for a quadratic equation is that it cannot be factored over the rational numbers. So we don't know for sure here that there aren't solutions to this equation. We just know that we're not going to be able to find them using our integers. Because if we go ahead and graph this equation, so here I've taken this equation, I've identified the axis of symmetry is at x equals 1. Then I took that back in and found the y coordinate for my vertex. So I can go ahead and put my vertex on the graph. 1, 1, 2, 3, 4, 5, 6. Okay, so I have 1, negative 6 right there. And then we'll put together a function table. Okay, and I picked 2 points on either side of my vertex. So I'm going to do negative 1, 0, and 2, and 3. And we can practically do this in mental math here because it's pretty easy. I got negative 1 squared is 1. Negative 2 times negative 1 gives me positive 2. So I have 3 minus 5 gives me negative 2. I put in 0, gives me right to negative 5. I already know my vertex. I put in 2. 2 squared is 4 minus 2 times 2. It gives me 0, and I'm back to negative 5. And then I put in 3. That would be 9. Minus 6 is 3. Minus 5 is negative 2. Okay, so that's looking good. I've got the pattern on both sides, and I can go ahead and graph those. 0 is negative 5. X of negative 1 is negative 2. X of 2 is negative 5. And x of 3 is negative 2. Okay, so now you'll notice, remember we said that this cannot be factored. If we go back to this page, we couldn't find any factors. We thought the trinomial seemed prime, can't be factored over the rational numbers, and yet when we graph this parabola, it does in fact have 2 x-intercepts. So it does have 2 solutions, but we just can't find them using our factoring. Okay, so when we have a situation like this, we're going to write cannot be factored over the rational numbers, but knowing in our head there may be solutions that we're just not finding. Next, let's talk about quadratic equations that may include radicals. So sometimes as you're going about trying to solve a radical equation, which we already know how to do, you'll end up with a quadratic equation. So as we square both sides here, we end up with x squared equals x plus 6. And if we put that into standard form, we've got x squared minus x minus 6 equals 0. So to find the solutions here, we need to go ahead and factor it. So we'll do a little factor sum table. We're looking for factors of negative 6 that sum to negative 1. So we're going to think about negative 3 times 2. That gives us negative 1. And we write out our factors, x minus 3, x plus 2. And remember, since we're equating that to 0, one of those has to equal 0. So then we go ahead and find the 2 possible values of x. Taking x minus 3 equals 0 gives us x equals 3. And then x plus 2 equals 0 gives us x minus 2. So those are our 2 possible solutions, but we cannot conclude their solutions until we have checked them back into the equation. So let me clear some space here. Okay, we're going to put them back in now. The original equation, so I have 3 equals the square root of 3 plus 6, and then I have, let's see, that was equals negative 2, right? I have negative 2 equals the square root of negative 2 plus 6. So let's see where this takes us. 3 equals the square root of 9. 3 equals 3. That checks out. Over here, I've got negative 2 equals the square root of 4. No, that does not check out. So negative 2 is what we call an extraneous root, so it does not actually work, even though it came out when we were solving the quadratic equation. So then our solution set here is just going to be 3. Okay, for your try these, do number 1 through 4, and remember you have to go back and check the solutions to make sure that they actually work.